Hey guys, what's up? Eddie Yahoo here with KissAnalog.com. Alright, today we're back at the Class A amplifier. This guy that was spec'd out at 20 watts. Only put out almost 8 watts. Well, I've done a series of videos on this, and if you followed along, that's awesome. If not, I'd recommend going back and looking at those other videos. I did, I think, 3 of them now. First one was a Boldy plot, pretty cool. Saw the THD Boldy plot 1 watt. That's usually what amplifiers are based on. But then I tried to take it up to 20 watts. Second video showed that it just didn't get there. And I tried to kind of explain why, but in the third video I think I did a better job at showing why it wasn't quite working. Okay, now in this video what I want to do is show that we can get 20 watts out of it. So thanks guys for suggesting I keep working with it. Typically, normally I would. I mean, you know, that's part of what we want to do in this channel is learn, right? But I'm trying to get an amplifier built, and I was just hoping that that's why I got a pre-built board just so I could plug in and play and build it up and give it to a friend. But it didn't work out that way. So, and also these Class A's, these are some of the more expensive boards I've bought. You know, like I think I paid close to like in the $90 range, 97 bucks or something. I think today you can get them for $75. So I'll put the link down below. But I'll show you how I fixed it. Okay, so let's come over to the bench. I'll show you what I did, and then we'll look at the signals here on the scopes, and we'll listen to some music too. And you can see how loud it gets. Okay, so, and then we're going to talk a little bit at the end just to kind of summarize. All right, so here, let me show you a board, my board, before we go. I want to show you some math, kind of how we fix this thing. A lot of stuff here. Let me just walk you through it. This is a 20 watt Class A amplifier and 8 ohms. Okay, that's very little information, but they do give some specs. Okay, it failed. It clipped too soon. And normally an amplifier clips because the output voltage rails starts to hit those. In this case, it wasn't because of that. It was because of the input stage. Kind of a regulation stage they have going on. And I showed a schematic in the last video, what that looks like. But, alright, so what I was getting is pretty close to 11 volts on the rails, and when you figure RMS power from that, you get about 7.8 volts. It wasn't quite 8 volts. That's why I say it's just below 8 watts. So power is V squared over R, right? And if we're only getting that much power, we square that, divide by 8. Math is really easy if that was 8. That's why I say it's almost 8, because 8 squared over 8, 8 times 8 divided by 8, it's just 8, right? So, but it's just a little bit below, so I put that line underneath the 8. Alright, so what do we need for 20 watts? V squared over R is equal to 20, so R times 20 is equal to V squared, right? But then you take the square root of that, and you end up with this. So 20 times 8, square root of that is this, and that's RMS voltage. But the rails, the peak voltage has to be square root of 2 times that. So it's 17.9 volts. So you need basically 18 volts. Say plus or minus 18 volts at the rails. And you need a little bit more because you need a little headroom, right? Here, let me show you my board again. Alright, and here we go. My magic board. So we were saying we need plus or minus 17.9 volts, right? And if we're gonna get a signal that can swing that high, that's what our rails would look like, and our well, that's where our peaks would go. Our rails need to be a little higher, right? Because there's gonna be some dropout, the transistors on the output circuit, and in this case, even that op amp up front, the preamplifier, I guess, the first stage of amplification, it's what caused the problem last time, and so we got to make sure that we can get this rail. So first, can we get this 36 volts peak to peak? Okay, if we could do that, then what voltage do we need to get this? Do we need something more than 36 because there needs some dropout. So is plus minus 22 good? There's a lot of transformers that come out with plus minus 22 volts. I have one, and I think I have another one that's plus minus 25 volts. So, you know, which of those will work? Or do we need something higher? So let's come over here to the bench. I'll show you how we're going to get this, and then, well, let's test to make sure we do. Now, I think we get real close to this. Let's see how close we get, okay? But much better than what we had before. All right, let's do it. All right, so let me just show you what I did here. Now, first of all, this heat spreader gets mounted on a heat sink in the box that has big fins on it. So we're going to have a lot of cooling once we get it in the box. That's the input over there. So I've got a differential probe in the input signal. And then over here is the output signal. Right down there, it comes off this air core coil. And it's coming right here. And I use these cool little lock things. And I am going to put a link down below for those things, guys. And they are really cool. I mean, when you snap in wires, they stay in. And it just makes it really easy to do stuff like this on the bench. And I have another one over here for the ground. So I've got the plus minus voltage rails and the ground right here. And this ground is for both the speaker ground and for the input power ground. Okay, so there we go. That's our setup. Now let me just zoom in right down here. See those little BJT transistors? They help set up some regulation circuit for this op amp over here. Okay, so let me just zoom in on that. You can see how I just kind of got them tacked in. I don't have them placed down on the board real nice and neat yet, because first I just wanted to test them before I go that trouble, and then it's hard to get them out when they're, you know, soldered all the way down. So they're just kind of tacked in the two positions. Okay, and they're 22 volt Xeniers. And by the way, I went on Amazon to buy these. It's so cool that you buy all of your parts on Amazon, but these are 1/2 watt. It's a nice little kit. You can see there's part of a taping rail that they've cut off, you know, so many diodes, and they're all marked nicely. So yeah, there's that one. And then I also got the 1 watt, and that's what I ended up putting in here. I bought them both just so I'd have them around here, and I decided to put the 1 watts in, so I put these guys down here. And this is packaged a little bit differently. They're individually, you know, packaged in their little boxes here. So I'll put links to those on as well. It's a free way to help support the channel. I appreciate it. Alright, here's our input signal, the yellow one, and it's 200 millivolts per division. The blue is our output, 5 volts per division, and this is our output current, 500 milliamps per division. And I've got these measurements down here, RMS for each one of them. I also have frequency for, you'll see it's a 1 kilohertz signal we're going to eject, and I'll bring up the power rails to plus minus 22, and then we'll bring up the signal and see when we get clipping on the blue. Okay, so you're going to hear my power spike come on. Alright, I'm going to bring it up to plus minus 22. Whoops, where's my safety glasses? There we are. And I'll start bringing up the input signal. Alright, and by the way, you can see the blue and yellow, that's the input and output. Input yellow, blue output, and the green is the current, and it's slightly out of phase with that. It's supposed to be a non-inductive load, but maybe I should test that resistor. Here, let's bring it up until we see clipping on the blue waveform. There we go, we're clipping. Okay, now just down here, we're at 0.045% distortion, THD. As I bring it up, I'm watching the distortion. Oh, right there, it jumped way up. Okay, down here it's good. Okay, now I can get a little more resolution on my generator. Right there starts to jump up, so right about there. And right here we're at 12.29 volts RMS and 33.7 volts, so we're almost at 20 watts. We're pretty darn close. Here I can inch it up a little bit more. Okay, yeah, I'd say right there. So 12.37 and 33.9 is about the max we get with 22.2. So you know what? I'm going to put my voltage rails all the way as far as I can go, 31.6. Okay, let's bring it up some more. See if we can. Looks like we can. I'm inching it up pretty slow. Maybe I'll go a little faster. Okay, right there. So right about there is where we are now. So we're at 0.05% distortion and we're at 13 volts. So it looks like if I bring my voltage rails up, I can do it. So now the op amp is not limiting us. We're getting the power out. So that's pretty awesome. And we're just getting warm on the heatsink. We got 1.58 amps out, or out of the power supply, and 1.47 right here going to our load. So it's looking pretty good here. The second question is, what do the voltage rails need to be? Let me drop the voltage rail down, 31.6 right now, and I'll watch the distortion and see when it goes up. Okay, right there, it's just barely starting to go up. I'm at 29 volts right now. So it looks like we need plus or minus 29 volts to get our 20 watts out. Or maybe it's slightly more than 20 watts. It's 13 volts RMS and 35.9 volts peak to peak. Right here's peak to peak, right there, RMS. Wow guys, it looks like it's working and the distortion looks really good. Now here, I'm going to go ahead and bring up the signal just to tell you what THD looks like on the screen. Okay, right there we're at 0.1 and you can barely see any clipping here at the top. Okay, I'm bringing it up a little bit higher. Okay, we're at 0.5% distortion. That's 0.5. So a little bit of flat on there is 0.5%. And we're 13.26, 36 volts peak to peak. I'll bring it up to 1% distortion so you can see what that looks like. Okay, there's 1% distortion. Now, you notice the bottom's not peaking out yet, just the top is. So we have a little bit more room on the negative rail. Well, that turned out to be a fairly easy fix. That op amp, being rated for plus minus 22 volts was enough. And Zener diodes come in 22 volt categories, so that was great that that I could get 22 volt Zener. Now with that voltage drop and the base emitter junction and the transistor that's regulating, it drops it down a little bit, so we're not operating right at the max of the op amp, but that's okay. It's designed to operate at 22 plus minus 22 and we're just below that. Well, the other thing is, the distortion was pretty low. Now I've got, kind of a rat's nest of wires, so it might look a little bit better when it's all cleaned up and the signal coming into it and all that is, routed correctly and short and all that kind of stuff. So could get a little bit better, but 0.05 I think is pretty darn good. And it's actually a little bit lower than that at some levels, and I need to do some more testing to see how it is at different frequencies and at different power levels. But for this video, it looks like it was successful. THD looks good. Like I said, now with just a little bit of clipping, just barely, it goes up to about 0.5 or 1%, and then you can get over 20 watts. And without, just before clipping, where the THD is real low, it's just a shade below 20 probably. But it's so close to 20 watts right now that I think we're good to say it's 20 watt amplifier. And in testing that, I put this 200 watt resistor, this aluminum resistor on top of that, heat spreader, heat sink, whatever. And that by itself, sitting here at the bench for just a few minutes each time I test, it's enough. Now if I sit here for 10 minutes, it gets hot and the bias current starts to drop after a few minutes, or probably, well, I don't know, I haven't really timed it, but I would say that I've ran it for 5 minutes at a time without it getting too hot, without the bias changing. This thing that makes all the difference, just having another mass that the heat can soak into and spread a little bit. But there we go. So what's left? Oh, a listening test. So, all right, hey guys, I'm gonna bring a speaker over and hook it up, and we'll play some YouTube music. And oh yes, and I am gonna bring over a new speaker. This speaker back here, I brought in Eclipse that I have, and it sounds just way better. This one right here does kind of sound a little muffled, and it's a center speaker. It's meant for a center stage, and yeah, I don't think it has, and who knows, it could even have a blown driver for all I know. It doesn't sound like it, but it doesn't sound quite clear. I did read online that some people say they lost a tweeter, and right now I haven't taken the time to test it to see if there's one of the drivers gone. So I'll do that too, but just trying to get this video done. I brought in this clip speaker, and it sounds pretty darn good. So I'll put it right here, and you'll see the top of it. And we'll crank this bad boy up using my Bluetooth board that I'm also going to do a review on. I've got a few of them actually, and some of them have that voice in front where they talk about, you know, it's, some people don't like that voice that comes on, if you know what I'm talking about, and some don't. This one doesn't. So, alright. Hey, thanks for watching, and thanks for the thumbs up last video that got me to do this. And let me ask you this. Should I do a video on Class A, Class AB, where I just kind of explain the difference and how to set the bias current? Is that helpful? Maybe I should do that. Alright guys, I have this big old clip speaker here, and it's hooked in. I'm going to turn on, the power supplies are running, that's why you hear the fan noise. This is running the Bluetooth app, which is really cool, hooks up great. And this guy is going to be our voltage rails. So I'm going to go ahead and bring it up, and I'll start playing some of this free YouTube music. I didn't spend a lot of time. I tried to find something quick, but something that had maybe some voices and, you know, some music that might test the amp. So here, let's go ahead and turn it on. Okay, let's go ahead and bring it up. Wow, I already got it playing. Here, let me bring down the volume. Okay, here we go. That's nowhere near clipping. That's pretty good, right? Pretty loud. Facing this way. So by the way, I listened to Stairway to Heaven because it's really quiet, and then it has these high peaks. Sounded awesome. Now, the one thing with, you know, 20 watts is you only do have so much voltage to go up in peaks. So when you're listening to something like Stairway to Heaven, you know, music where you have some really quiet, really nice music, and then all of a sudden some, you know, high notes, some big amplitude things, the dynamic range does make a difference. So I put a 150 watt amp on this, one of my 150 watt amp cards, and it just does sound nice having that dynamic range. But for 20 watts, when I play this and keep it from, I watch the scopes, make sure I'm not getting clips, you know, some music notes that are flying up. The overall average power is not 20 watts. That's the thing. That's like a bench power test when you're putting a sine wave in. Real music's nothing like that. So the average power, you know, the RMS, what people call RMS power, which is a misnomer, it's just power. It's average, it's really average power. But you take RMS voltage, RMS current, multiply them together, you don't get RMS power. That's like double dipping in the RMS terms. Anyway, you know, when you get your power out at 20 watts, it's that's a lot of sound. So, you know, when I'm watching this stuff, it's down to low wattage, and then you get these high wattage transitions, these dynamics in the music, and that's what we want. So really you want dynamic range, and that's why I think, you know, I've kind of mentioned before, I think the way we specify power on amplifiers is just wrong. It doesn't give the true sense in what music does. And doing bench testing with 1 kilohertz, 10 kilohertz, whatever frequency you want, is, you know, it is a data point, but it's not the data point that's of importance. So there you go. There's my soapbox. All right, we'll talk more about that as time goes on, I think, and I'll show what I'm talking about. But for now, it looks like this resistor is pretty hot. My heat sink, oh, it's kind of chilly in my lab, so it feels good. But yeah, I had it playing for a little while, and it does heat up. So it does, that heat spreader, what some people call it a heat spreader, I think it's maybe a better term. I was calling it a heat sink, you know, semantics, I guess. But that goes on, the metal box I have has fins all the way down the sides, and one of these would mount on each side. That would be the idea. So, alright guys, looks like we fixed it, and thanks for, you know, giving the old thumbs up and saying I should do it, because it seems pretty good, and those transistors, they seem like they work well. I don't see the distortion increasing with power, not really, but then again, I haven't done a full test. So do you guys want to see that? Should I do different power levels at different frequencies? Let me know. Oh, and also I was using the Spectrum, and hey, let me turn on the music again and watch the Spectrum analyzer if you can see it back here. You know, I don't know if you can tell from there, but this frequency span is 10 kilohertz across here. I'm only looking at the 10 kilohertz range, but the low kilohertz, these first few kilohertz, that ramp just kind of ramps up. So what it tells me, there's a lot of frequency content. You know, there's music at all kinds of places within these low frequency bands up to the few first kilohertz, and that is like wide band. I mean, it's not just one or two frequencies, there's a lot of them. We'd see spikes if there's just, sometimes in some portions of the music I'll see just spikes, you know, popping up where there's maybe a drum or a different, you know, violin or something like that. But when you got a lot of instruments going on at the same time, then you kind of see what we saw there. So interesting when you start looking at what music looks like. Alright, hey, thanks for watching again, and we'll see you next time.